So Lena tells me to, that as an announcement, you all should check out the Arizona Winter School, which is a great gathering it takes place in March.
Yes, beginning of March.
Beginning of March, early March, and you sign up online. And the topic this year is ewasolitary. And I think John Coates is going to be one of the lecturers. It's a good thing to learn. So you have to sign up and apply, and it's really a great opportunity to meet grad students from all over the country in number theory. That's the whole point of it, really. Okay, so today we're going to get to a statement of what's called Dirichlet's class number formula. And it's a formula for the residue at s equal 1 of the zeta function of a number field. And so last time I defined the zeta function of a number field. So it's really associated to the ring of integers in the number field. We saw that for a number field, which is a finite extension of irrational numbers of degree n, it contains a natural ring, which is a free Z module of rank n, called the ring of integers. And that ring has a lot of properties similar to the integers. For example, every non-zero ideal has finite index. And the zeta function is just a way of counting the number of ideals of each index. So it's the sum over the ideals of the ring of integers, which are non-zero. And for each ideal, you put in 1 over its index squared. And the index is frequently denoted by the norm of the ideal. But it's just defined as the index in the ring of integers, and you take that to the s power, and that converges, just like the zeta function, for real s greater than 1, and it has an Euler product. We saw last time, because every ideal is uniquely the product of prime ideals, minus the norm of p, minus s inverse, so just like the Riemann zeta function. And the Riemann zeta function we saw had a residue of 1 at s equal 1. So it had a simple pole at s equal 1. The residue was 1. And it's more complicated for the residue of the zeta function, but that's a really beautiful formula in number theory, which has stimulated a lot of other work. So I'll describe it to you today. And then since Dirichlet didn't know what the zeta function is of a number field or its Euler product or anything like that, I'll try to describe to you why it's called Dirichlet's class number formula, because he proved a very special and important case of it. Okay, so that's the first persona. Now, this residue is going to be given in terms of invariance of this ring A. So in terms of, that's what's so cool. I mean, here you just have a function that just determines what the different prime ideals are, or the different ideals of a given index are, and it knows all about various arithmetic invariants of this ring. So the last time I defined 2 of the invariants. One is the discriminant of A, discriminant of the ring A, which is an integer which is non-zero. And it's defined as the determinant of the Graham matrix of the trace form. So you choose a basis for A over the integers. And then you take the determinant of the n by n matrix given by the traces of the products. So these are all integers. So the determinant is an integer. And it's well defined because if you change your basis for the ring of integers, you choose to replace the alpha I by an equivalent basis beta I. The bases are related by an invertible integral matrix. And when you calculate this trace matrix, you multiply on one side by the matrix and the other side by its transpose. And since the determinant of an integer matrix is plus or minus 1, when you multiply this by the determinant of the matrix and the determinant of the transpose, you get 1. So the discriminant is a well-defined integer, has a number of nice properties, I said last time. For example, it's always congruent to 0 or 1 mod 4, that's a nice exercise in rearranging this matrix. And another nice property is that the sign of it as an integer is -1 to the R2, where R2 is the number of complex places. So I also said that last time, that if you think of k over the real numbers, so you think of this as an extension of the real numbers, that's a real algebra of degree n, and we know the classification of algebras over the reals, and it has to be a product of a number of copies of the reals and a number of copies of the complex numbers, because the field extension of the real numbers is just the reals of the complex numbers by the fundamental theorem of algebra. And this R1 plus 2 times R2 is equal to the degree of the field, because it's the dimension of this is a real vector space. And the sign of the discriminant is -1 to the number of places, complex places. So these are two general facts about the discriminant. In any case, it's an integer. And, okay. And the second invariant we defined as a positive integer, the order of the class group A. Okay, and that's by definition the quotient of the group of all ideals by the subgroup of principal ideals. So those are the form alpha times A, where alpha is an element which is non-zero in K. That gives a fractional ideal. And it's not the case that every fractional ideal has this form, like the rational numbers, but a big theorem is that this quotient group, this ideal class group, is finite. You have to prove that. That's one of the fundamental theorems of number fields. And so since it's finite, you have a formula, it's ordered. Okay, so the final ingredient, so those two invariants appear in Dirichlet's class number formula, and the final ingredient that appears is related to the units. So as I said, there's an exact sequence that goes like this: K star to the principal ideals, the principal ideals, all ideals, and the class group. That's one exact sequence. By the way, this group is extremely simple. It's just the direct sum over all primes of z times p, because every ideal is uniquely the product of prime ideals, and only finitely many primes appear in each ideal. So this is just a free abelian group on infinitely many generators, and the complication is that this is a complicated subgroup of it. But p also fits in an exact sequence. Namely, it's the quotient of k star. Every principal ideal is generated by some element, and the elements that generate the trivial class, namely the class of the ideal A, are just the units, elements in A star. And the final invariant concerns the unit group. And Dirichlet's unit theorem, which again he didn't prove in general, he proved for quadratic fields, is that the structure of A star is a free abelian group of rank R1 plus R2 minus 1, and a cyclic group. So it's finitely generated. Not generated. It's not only finitely generated, but it gives the rank in terms of the number of real and complex places, and it gives the torsion subgroup, which is cyclic, and W is equal to the number of roots of unity, which is usually 2. If, for example, over here you have one copy of the real numbers in this, then the number of roots of unity is 2. Okay? But you need more than the structure of A star to do the class number formula. You need somehow how this is proved. And that's just as interesting. And so to do that, I have to introduce a little bit more evaluation theory, and we'll get back to this when we do the adels and edels of a number field. Okay, so evaluation of a field is just a homomorphism from the multiplicative group of the field to the positive real numbers. So assigns to every element non-zero in the field a positive number, and it's a homomorphism, so the valuation of a product should be the valuation of alpha times the valuation of beta, and it should satisfy the triangle rule that this is less than or equal to the absolute value of alpha plus the absolute value of beta. So a typical valuation is the absolute value on the real numbers. Which takes a number alpha and it takes it to alpha times its sign. We call that the absolute value of alpha, and that satisfies this by the triangle law. Okay, another typical valuation is on the complex numbers. You can take the complex numbers and you can take them to the positive real numbers. And for example, you could take an alpha to its complex absolute value, but I'm actually going to take it to alpha alpha bar, which is what they usually call the complex absolute value squared. That satisfies these two properties. But there are other valuations on a number field that come from its prime ideals. So these two valuations for a number field give R1 plus R2 different possible valuations, because if I, for each embedding of this algebra, I can embed this algebra into R, or I could embed it into C. And there are two ways of embedding it into C, up to conjugation. And if you conjugate on C, you get the same valuation. So you only get R2 different valuations of it from the complex embeddings and R1 valuations from the real embeddings. So that gives a finite number of what are called the Archimedean valuations. So this gives R1 plus R2 valuations on K star at infinity. And if you take the product of, I'll say, valuations, I'll write them like this. So V. So V refers to one of these real embeddings or one of these pairs of complex embeddings. And if you take the product of all of those over R1 plus R2, and you take the absolute value of alpha, so V, what do you get? Well, you get the product of all the, think of this as, when you embed an alpha into R, you're having an alpha, and when you put it in here and then decompose this way, you're taking the real and complex roots of the equation satisfied by alpha. And you're taking the product of all those roots over the real roots, and over the complex roots, you're taking the root times its complex conjugate. So you get all the roots, and then you take the absolute value. So it's the product of all n roots of the characteristic polynomial of alpha, the usual absolute value in the complex numbers of that root. You know, where the absolute value is this. And when you do that, the product of all the roots is the norm of alpha. So you're getting the absolute value of the norm of alpha. Okay. That's why I've set it up this way. So that, I mean, you only have R1, R2 embeddings in the complex numbers, but for each one you're getting somehow the root and its conjugate. You take the product of all those. Okay, but as I say, for number fields, there are more valuations that come from the different prime ideals. So for each prime ideal, P, in the ring of integers, get a valuation which I'll call alpha sub P. And the definition of that, and you might wonder why you do this definition, but you'll see in a second. You take the index of the ideal and you raise it to to the power of p that divides alpha, which is some integer, positive or negative. So if p divides alpha, so alpha, remember, the ideal alpha is the product over p to the order p of alpha. Every ideal factors. So you see what power of the prime divides it. It could be a fractional ideal, so it could be a negative power. You take this positive number, this is of course some power of p, because we saw that any ideal was a finite, any prime ideal in A is a finite index, and therefore the quotient is a finite integral domain, hence a finite field, so it has a characteristic, and therefore this contains PA for some prime P, and the index of this is P to the n. A is a Friese module of rank n, so this index has to divide it, so it has to be some power of P, where this power of P is less than the degree of the number field. So this is a power of P to a negative integer. So that's a positive real number, and if you multiply two alphas, you add their valuations, they're ordinal. I mean, if you multiply alpha times beta, you can calculate its prime factorization. If you know the prime factorization of alpha, you just add these. So that means you multiply these. And so that's this property. And this property holds in a very strong way, namely it turns out that the absolute value of alpha plus beta to the p is actually equal to whatever it is, the minimum of the maximum is equal to the minimum, yes, of the absolute value of alpha p, beta p, because the power of prime that divides, wait a minute, it's less than or equal to the maximum?
Yeah.
Yeah, that's better. Maximum, because the power of p that divides this sum is, if they have different powers of p, it's equal to the minimum power of p. And then because of this minus thing, you get the maximum. And then it could be a little bit larger if they have the same power of p. It could be another power of p, but then it's bounded by this. So that's called the non-Archimedean property. In any case, this is a valuation for every different prime p. And if you think of it, for a given alpha in K star, almost all of these are zero because it's only divisible by a finite number of primes. All the others of these terms are zero. So it makes sense to take the product over all primes p of the valuation of alphas of p for a fixed alpha, because almost all these terms are one. So it's really only a finite product. And what product is it? Well, I claim it is, you're taking the product over all primes p, so you're getting the product of norm of p minus ordered p alpha, and right, and that turns out to be 1 over the absolute value of the norm of alpha, because if you take, I mean, the norm of alpha is the norm, the index of this ideal is the product over all the primes dividing it of p to the this. So that's just the norm of alpha. And consequently, if you take this times this, then it's equal to 1. And that's the famous product formula. And we're going to use this later when we do the Adels, that for alpha in K star, the product over all valuations, the absolute value of alpha b, is 1, because this breaks up into the product of the infinite valuations, which gives you the norm of alpha, and the product over all the finite valuations, which gives you 1 over the norm of alpha. So they cancel out. Okay, now you can rethink a lot of the theory of the rings of integers and the units, etc., in terms of these valuations. For example, when is alpha, which is non-zero in K, an element of A. Well, that would mean that the ideal it generates, so then the ideal generated by alpha is contained in A. So that means that OR P of alpha is greater than or equal to 0 for all P, right? Which is equivalent to the absolute value of alpha P less than or equal to 1 for all P. So it's in some kind of, so if you embed the field K inside the product of all the completions at prime A primes P, and you can complete with respect to evaluation, we're going to get into that later, then the ring of integers goes into the unit wall. Okay? What about being a unit? Well, then you want, pardon? So it's something as a unit if it's not only an element in A, but its inverse is in A. But the inverse of this is 1 over alpha. So we find that alpha is a unit if and only if the valuation of alpha P is equal to 1 for all primes P. Namely, it generates the unit ideal. Okay. And consequently for a unit, then we know that the product of the alpha V, or V dividing infinity, is equal to 1. Well, because the norm of any unit has to be a unit of the integers, and the units of the integers are plus or minus 1. And this product is the 1 over the norm, and so it's 1. So we're going to use this. Now the individual valuations in infinity are not necessarily 1. So if you take the simplest example of a unit, is if you take cube square root of n, where n is some positive number, which is integer, which is square free, and you take a solution of Bell's equation, which has been also studied by Euler, and earlier that Euler by English mathematicians, not Pell. It's a misnomer, Pell's equation. So solution of Pell's equation is something of the form x squared minus ny squared is 1. And you take alpha to be x plus y square root of n, which is certainly an algebraic integer in K, because it satisfies an integral polynomial with integer coefficients, then that's a unit in K, because its norm is 1. Alpha times alpha bar times alpha prime is equal to 1, so a unit. Its inverse is its conjugate, and well, that doesn't have the absolute value of alpha. There are 2 infinite places. Infinity 1 times the absolute value of alpha at an infinity 2 is equal to 1 by what we've just said. There are two infinite places, but at the individual infinite places, it just has the absolute value of this real number, where you have to choose a real embedding of square root of n. So at one point it's a positive real embedding, and the other point it's a negative, and those give you the two valuations in infinity. So Dirichlet is going to use the fact that the product is 1, but the individual alpha v's are not usually equal to 1. Okay, it turns out that if all the valuations are 1, that's when you get the roots of unity. So that's a theorem of Kroneker's. Kroneker. Says that if alpha in A star has alpha b equal to 1, all b dividing infinity, and consequently for all valuations, then alpha is a root of unity. And roots of unity have that property because no matter how you embed them in the complex numbers, they end up on the unit circle. They're another root of unity, and anything on the complex unit circle has absolute value 1. Okay, so Dirichlet is going to use the fact that these infinite valuations are not equal to 1 in some sense to get the structure of the unit group, and I'll show you how he does that. Sure.
Because I think, if I remember correctly, there's theorem says there the infinite solutions of Pelt's equation.
Yes.
And then in this case, can you find the canonical generators for the group of units?
In this case, you can, through Pell's equation. I'll get back to that. So I want to, that's a good question, because I want to stress this. This is one of the fundamental open problems on number fields, which is extremely frustrating, and which Professor Stark, who's here at UCSD, made his lifetime work around, which is the following problem. For real quadratic fields, we have actual constructions of units from the theory of continued fractions. One takes the continued fraction of square root of n, one finds it's eventually periodic, one chops it off at the period, one reconstructs a number which is the solution of Pell's equation. So one has a construction of units, and in this way, since the unit group in this field, by the way, here R1 is equal to 2, and R2 is equal to 1, so the claim on the rank of the unit group,
R2 is 0, right?
R2 is equal to 0, thank you. And the rank of A star is 1, and in fact, A star is isomorphic to the powers of some unit, epsilon, cross plus or minus 1. The roots of unity are plus or minus 1 because it has a real embedding. So maybe epsilon to the z. And we know how to construct this epsilon. It's not exactly this, but one knows how to construct it with continued fractions. In the general unit theorem that I'm going to describe to you today, one does not know a construction of the generators of that group. There are some special cases where one can construct subgroups of finite index in that group. One has generators of subgroups of finite index. But even that is too hard in general. And well, when we get to Artinel functions, I'll tell you what Stark's conjectures are on this. They're really fascinating. But it's a fundamental problem that we don't really know how to construct units, except for real quadratic fields. Okay, so what did Dirichlet do to study units? And he constructed something now called a regulator. Go over here. Can you guys, maybe I'll Gives me more black. Anything for more black. Regulator map. So the regulator map is going to be a homomorphism from the unit group to a real vector space. And the real vector space is going to be canonically the sum over v dividing infinity of r times a basis vector EV. Or as a real vector space, it's going to be r to the r1 plus r2. So it's the free R module generated by the places dividing infinity. And here's the map. You take a unit epsilon, and you map it to the sum. So you have to put a real number for each basis vector for v dividing infinity. And you take the absolute value of epsilon v, which is some positive real number, not necessarily 1, and you take its log. And by log, I mean the integral of 1 over x, that log, and at times the basis element. So the coefficients are these logs. So they measure exactly what the valuations of the unit are at the places dividing infinity such that the product of them is 1. And note that the log gives an isomorphism from r star plus, which is where this thing takes values, to r plus. Right? That's the additive group of real numbers. It's a little easier in Dirichlet's case to work in the additive group of real numbers than the multiplicative group of positive real numbers. Okay, that's the map. And it's a homomorphism precisely by the properties of valuations, namely, if I apply it to epsilon 1, epsilon 2, the valuations multiply, so the logarithms add, right? Log of xy is log x plus log of y, and that occurs for each basis vector, so it's an addition law in this real vector space. And the kernel of that map are the units where the logs are all 0, and consequently the values of these epsilons are all 1, and by Kroneker's theorem, which was known to Dirichlet in this special case, that's the root of unity. So at least for this homomorphism, we know the kernel of lambda is the roots of 1, and they form a cyclic group in any field, so I'll write that as the mod WZ. W is the number of roots of unity. And the whole question of the unit theorem, etc., is what is the image? Well, first of all, we know one thing about the image. The product of these values over all the places is equal to 1. And so the sum of their logs is equal to 0. So it lies in the hyperplane H in R to the R1 plus R2, where these are the vectors sum of AV, EV, such that the sum of the coefficients is 0. So it's in the kernel of that linear form by the product formula. Okay? Okay, and the hard part of the unit theorem, which Dirichlet gave an argument for and Dedekind extended, okay, so unit theorem in its refined form is that the image of lambda forms a subgroup of this hyperplane, which is both discrete and co-compact. So it gives a lattice in this hyperplane. And it's known if you're in a real vector space, this is a real vector space, isomorphic to R to the R1 plus R2 minus 1. And if you have a subgroup of that globally compact abelian group, which is both discrete in it and co-compact, namely the quotient is a compact group, then it's known that that image, so image is free abelian of rank R1 plus R2 minus 1. That's the only way you can get a subgroup which is discrete in both and co-compact. And that gives the full structure of the unit group, namely its quotient by its torsion subgroup, the cyclic group, maps isomorphically onto the image, which is discrete and co-compact in this hyperplane, so it has to be isomorphic to that. Doesn't give the construction or anything. Of course, in the proof of this theorem, to prove that the image is large, namely that the quotient is co-compact, so that you have at least this many independent units, is hard work. The discrete part is easy, but then you have to construct something. But you prove this by constructing units where one of these AVs is positive and all the rest are negative. Namely, where one of these epsilon V's is greater than 1 and all the others are less than 1. Notice that that's the case in this business because one of these has to be bigger than 1 and one has to be less. But when you have n of them, you have to make a real construction. And that uses geometry of numbers, and that would be another very good topic for a paper, you know, for undergraduates, for a particular, a proof of the unit theorem. So that's in every book on unit theorem. Okay, but it gives a little bit more, because when you have a real vector space and a subgroup in it, which is co-compact, then you can take the volume of a fundamental domain for that subgroup on this real vector space, and this has a natural measure on it. You put the obvious measure on this because you have the basis vectors, and then this gets a natural measure as a hyperplane because the image of the linear form has a measure. And it turns out that the volume of this co-compact subgroup is called the regulator. And it's basically, you can also write it as the determinant, the absolute value of the determinant of the matrix, where you take these coefficients, log of the absolute value of epsilon I, at Vj, where you take this as to be a basis for the units modulo torsion. So A star is equal to the roots of unity cross the product cross epsilon 1 to the z cross etc. cross epsilon to the r1 plus r2 minus 1 to the z. So you choose a basis for the units modulo torsion, and you take their absolute values at all places but 1. So J runs from 1 to R1 plus R2. You ignore you throw out one valuation as hideous as that sounds, because once you know these numbers, you know it at the other place. So this is an R1 plus R2 minus 1 matrix. You take its determinant, that's non-zero, that's the fact that the units form a co-compact subgroup. That's an integer, because it's a real number, and you take its absolute value, so you get a positive real number. So the fact that you prove that they're both discrete and co-compact, that gives you the rank of the group, but it also gives you a certain volume, and that's called the Dirichlet regulator. And if you did that for real quadratic fields, R would just be the log of epsilon, where this number is a fundamental unit bigger than 1. And then the log of epsilon is positive, so you don't have to take absolute value or anything for real quadratic field. For the rational numbers and the imaginary quadratic fields, for the rational numbers, R1 is 1 and R2 is 0, so this is 0. For imaginary quadratic fields, R1 is 0 and R2 is 1, so this is also 0. And you say that the regulator is 1. The determinant of a 0 by 0 matrix you declare to be 1. I don't know. It's the product of over the empty set. Anyhow, that defines the regulator, and in the stupidest cases it's 1. In the first non-trivial case, it's just the log of the fundamental unit. Once you get to fields where the rank is 2, you're taking the determinant of a 2 by 2 matrix. Okay, so all that being said, I'll give you Dirichlet's class number formula. It says that the residue at S equal 1 of zeta k of S is 2 to the R1, 2 pi to the R2, over the square root of the absolute value of the discriminant. Remember, that's an integer, but not necessarily a positive integer, times the class number, times the regulator, divided by the number of roots of unit. What could you ask for? I mean, that's so nice. It's got all the invariants in it. And I should say that you have to take all of these things. So there are number fields that are not isomorphic that have the same zeta function. I mean, the zeta function is just an invariant. You might have two different number fields where you have the same number of ideals of index n, right? And not isomorphic. And people have constructed examples of number fields which have the same zeta function, but different class numbers. So the class numbers change, but then the regulator also changes. So the whole product of them has to be the same, but the individual elements. So it turns out that if k and k prime have the same zeta function, that implies that degree is equal to the degree prime, and that the R1 and R1 prime, R2 is equal to R2 prime, D is equal to D prime. So a lot of things are the same. W is equal to W prime. But H and R can change, just the product is the same. So this would also be a really good paper. So it's a little bit more advanced than the proof of the unit theorem. If you wanted to do both of them, even better. So the way this is proved is to estimate, remember that the zeta function is the sum over n greater than 1, bn n to the minus s, where bn is just the number of I of index n. That's all it is. It's a counting function in the rate of integers, n. And its residue is calculated using some simple transforms as you want to calculate this, or estimate the sum n greater or equal to 1 of Bn, for n less than x. You want to estimate the growth of this sum. For the Riemann zeta function, that grows like log x. Sorry, that grows like x, because Bn is equal to 1 for all values of x. All right. So you have to prove that this is a constant times x plus a term that's less than x, and in fact, what turns out is it's just a little less than x. It's O of x to the 1 minus 1 over the degree of k. So for quadratic fields, it's like x with an error term of x to the 1/2, but for cubic fields, it's a multiple of x, an error term of x to the 2/3, etc. The error term gets closer and closer to x the further, and this constant turns out to be equal to this number here. To this term. So first of all, you have to prove that whatever the constant appears here, that's the residue. And secondly, you have to calculate the constant. So that's how the class number formula is proved. And I'm going to do it for you in a really super special case. So you see why it's called Dirichlet's class number formula, because Dirichlet proved this for imaginary and real quadratic fields, which was maybe his singular achievement. Of all the great things he did, that must have been the greatest. And then Dedekind generalized it to all other number fields, generalizing Dirichlet's proof. And notice that you don't need to know anything about the analytic continuation or the functional equation or anything about the zeta function, because they didn't know that in the 19th century. You just need the fact that this series converges for s bigger than 1, and you can study it as s tends to 1, and this is what you find. Okay, so what does this look like? All right, let's check this in a couple of cases. Because the fun is when you can actually work out the class number formula and see what it says. Okay, for the rational numbers, it says the residue of the zeta function is equal to, well, let's take a look. There's one real place and no complex places, and the discriminant is 1. So this term here is just 2. The class number is 1, the field is a principal ideal domain. The regulator is 1 because there are no units of infinite order. The number of roots of unity is 2. So it's equal to 1. So the residue is 1, as is what we found. How about if k is q square root of d, where d is less than 0, imaginary quadratic? Okay, the residue is equal to, well, there are no real places, so it's 2 to the 0 power, that's 1. There's one complex place, so you get 2 pi, and then you have the square root of the absolute value of d, because d is less than 0, times h, the class number. The regulator is 1, because there are no units of infinite order, and the number of roots of unity, well, it's usually 2, but it can be 2, 4, or 6. And it's 4 if you have the 4th roots of unity, and 6 if you have the 6th roots of unity. But you see, it really gives a formula for the class number, because everything else is known. This is easy to work out, and this is known, and 2 pi is known. So it gives a real formula for the class number if you can calculate it. How about for real quadratic? So then the residue is 2 squared times 1 over the square root of d. And now you have h log epsilon, that's the fundamental unit, divided by 2. Because the number of roots of unity is 2. And so you get 2h log epsilon over the square root of d. And so it doesn't really give you a formula for the class number or for the fundamental unit, but if you knew what the fundamental unit is, you could work out the class number. Okay? And likewise, if you knew what the class number was, then from the residue you could work out the fundamental unit. Okay. Now remember that we proved last time, using the Euler product, that if we had a quadratic field, the zeta function factored as the zeta function of q in both cases, zeta k of s is the zeta function of q times one of these Dirichlet L functions, where chi was a quadratic character of this group. That was from quadratic reciprocity. So we therefore, this residue is 1, this residue is given by the Dirichlet's class number formula, so we find that the residue at s equal 1 of zeta k of s is the same as the value of this L series at 1. I mean, the only way that this product can have a simple pole, if this has a simple pole, is if this is regular at s equal 1 with non-zero value. And that's basically how Dirichlet proved that this value was non-zero. By comparing it, by using this formula, and then finding a formula for the residue of this at s equal 1, in these two cases, which I'll show you how we did it, and he gets this value. Okay. So finally, I have to say why this is called Dirichlet's class number formula, because Dirichlet did not know the theory of number fields, and did not have the ring of integers, and did not have prime ideals, and did not have class groups, and did not have unit groups, or anything like that. He worked in an ancient language, well, ancient, very useful language, due to Gauss, and he worked in, he only did it for quadratic fields, and he used the Gauss's theory of binary quadratic forms. And I'm going to show you, because it's important in the connection, and also binary quadratic forms are such beautiful things, and it's good to know the ancient language too, to replace ideals and ideal classes of quadratic fields, and worked with them. So Dirichlet used, so this you don't find in the book so much, because the theory of ideals and their norms and et cetera, and they've even been modernized to the theory of ideals, their norms, which we'll do, but it's good to see how it rose out of this edifice that Gauss had constructed. People sometimes say that binary forms are sort of ancient, but in fact, if you ever have to compute ideal classes, this is the way you do it. Okay, so what's a binary quadratic form, and how are they related to ideals? I don't know if I'm going to finish that today, because I got to quit at 12:30 to go to lunch, but we'll get there. Okay, a binary quadratic form is an expression like this. It's a quadratic form in two variables with integer coefficients. And just like for number fields, you have the discriminant of a quadratic form, binary quadratic form, and d is, as you think, b squared minus 4ac. And notice that that's congruent to b squared mod 4, and so it's congruent to 0 or 1 mod 4. So before there were number fields and discriminants of number fields, etc., there were binary quadratic forms which had a discriminant. And we're going to assume that this thing is positive definite. That's the imaginary quadratic case. So it only represents numbers that are greater than or equal to 0. And that means there are two conditions. One is that the discriminant is a negative number, so the roots of this thing are imaginary. And the second thing is that the outside, so that makes it definite. And if we want it to be positive definite, that means that A and C are both positive. Usually what one does, and we call a form primitive, if the GCD of ABC is 1. This is Gauss's notation. There's no common divisor. I mean, if there's a common divisor, then the square of that divides the discriminant. But anyhow, this is positive definite condition. Discriminant less than 0 and the outer coefficient is positive. Okay. So Gauss studied the action, well, Gauss and Lagrange, and then later Gauss studied orbits of GL2 of Z and SL2 of Z on the forms of discriminant B. So it turns out that if you think of this as a function on a free Z module of rank 2, it's really a map from Z squared to Z, a quadratic map, right? Where it's just all things in the form xe1 plus ye2, and you apply that quadratic form, you get this value, and positive definite means it takes positive values. So if you would get a different binary quadratic form, different ABC, if you changed your basis of this by an element in GL2 of Z or by an element in SL2 of Z. And it turns out that under a change of basis, the discriminant is an invariant. And namely, ABC changed, but the discriminant remains the same. Here, change of basis. So if you fix a negative discriminant, you can ask, how many binary forms are there of that negative discriminant? Well, there are infinitely many because you just keep changing basis and you get different binary forms. But you might ask, how many are there up to change of basis? So that would be the number of orbits of this group on the set of forms of discriminant. And Lagrange proved that there were finitely many orbits. But he was using the full group GL2Z. So you also get finitely many orbits under this subgroup because this subgroup has index 2 in this group. Remember here the determinant is plus or minus 1. So if you restrict to the subgroup of elements of determinant 1, you get also finitely many orbits, no more than twice as many for both. And it turns out, and that's one of Gauss's big discoveries, that it's much better to do the orbits of this group on a set of binary forms of discriminant D than to do the orbits of GL2. And Gauss proved, the big theorem, that every SL2Z orbit has a unique representative, which is, and this is how he proves finitely many orbits, which is called reduced. And reduced means the following inequalities, that minus A is less than B is less than A, which is less than C, or either minus A, the coefficients lie in that inequality, or 0 is less than or equal to B is less than or equal to A is less than or equal to C. So you can have equality, but then B has to be positive. Okay. Now, what does this really mean? And after we'll prove this, we won't prove the reduced representative, but once you have this theorem, it's easy to count the orbits and etc. So if you let tau be a root, like tau, is equal to minus B plus the square root of D over 2A. So that's in the complex numbers. Because I've taken the square root of a negative quantity. Okay, so then, and we'll take this to be the positive, so we'll say that square root of D is equal to positive real number times I. So it lies in the upper half plane. Okay, well then, first of all, we can recover this binary form. If I'm not mistaken, it's x minus tau y times x plus tau y. I mean, it's factoring this form in the complex numbers and maybe multiply by a. I hope that's right. That's equal to q of xy, I believe. Anyhow, let tau be that. What does reduced mean? Well, first of all, what is the real part of tau? Well, the real part of tau is minus b over 2a. Okay? So that's a number, so it lies between minus a half and a half, right? Because b is between minus a and a, so if you divide this by 2a, you get a number between minus a half and a half. Okay? And what about the absolute value of tau? Well, the absolute value of tau is b squared minus d over 4a, when you multiply this by its complex conjugate. And d is b squared minus 4ac. So this is 4ac over 4a squared. Oh yeah, I forgot to square this. B squared minus d over 4a squared. 4ac over 4a squared, which is c over a, and c is greater than a in both cases. So this is number greater than or equal to 1. So where does tau lie in the upper half plane? If you take the circle of radius 1, tau lies outside that. That's a poor picture, but never mind. And then you take from minus a half to a half, and you draw the straight lines up here. Tau lies inside of this region and outside of this region, so tau lies in this region, which is sometimes called the fundamental domain for the action of SL2Z on the upper half plane. So just the orbits of SL2Z on the upper half plane lie in the same region that give you the orbits on. And what is about these inequalities? Well, this says that if b is equal to a, means you're on this line, and then c equal to a means you're in here. So you have to have the boundary points which are on this line and here, and then if you take those orbits, you get everything. Okay. In the interest of my getting to lunch on time, I'm going to stop here today. We're going to come back. And show that once we have this, we'll show how to count the orbits, and then on Thursday I'll show you the relationship between the values of these binary quadratic forms and the norms of ideals in a given class for an imaginary quadratic field. And that way we'll be able to relate the zeta function of quadratic fields to these binary quadratic forms, which is exactly what Dirichlet studied. Okay, binary quadratic forms would also be a wonderful subject for a paper. There's been a lot of activity on it. I mean, as I say, this was a big theorem at the beginning of the 19th century in number theory, and then it kind of faded as people constructed ideals and said, oh, ideals are a better way to do it. But these integral orbits have come back into the game, and much studied by Manju Bhargava at Princeton and his students and whatnot. And Bhargava has all kinds of beautiful things about how you multiply ideals and things like that by studying integral orbits. So this would be a good introduction if you wanted to learn about Bhargava's modern theory to do Gauss's theory of, or Lagrange and Gauss's theory of the orbits on binary quadratic forms, if you like that for a paper. So I'll just keep throwing out paper subjects as I go along, and then maybe if I can remember them, towards the end I'll make a list of all the non-classical paper subjects. But if you want to get working on a paper and you're very interested in how you prove there are a lot of independent units, or how you calculate the regulator, or how you prove the class number formula, or how you do binary quadratic forms, you can get going right away. Okay, see you Thursday. Reminder, there's a number theory talk this week on Thursday, and Wei Ho will also give a pre-talk. And Wei Ho works in this area of integral orbits, So it ties in perfectly.